Hi, my name is AЩwietlicka, and today I will have a pleasure to talk about BiLSTM recurrent neural networks and heterogeneous ensemble models for named entity recognition problem and long Polish unstructured documents. I work at the Poznań University of Technology in Poland, but I am also a member of AI team in the Wrocław Institute of Spatial Information and Artificial Intelligence. At first, let me tell you about the agenda of today's talk. At the beginning, I will give a short introduction where I will describe the problem that we have tried to solve. Then I will explain the process of data preparation and our methods, among which are artificial neural networks and ensemble models. To sum up, I will present results and give a brief summary. In this research, we are facing a problem of information extraction and entity typing from long Polish documents with complex layouts, which was one of the PolEval 2020 tasks. Documents are financial reports of Polish corporations, which contain unstructured arrangement of text, such as very long tables, space for signatures, headers and footers, two-column format, and so on. For each of the reports, there were 3 files available: PDF, which contained the original report, text, which was the OCR of the report, and HOCR, data representation for formatted text obtained from OCR. In our solutions, we have focused only on text files, which we have noticed were very tidy and quite easy to process and prepare for further analysis with machine learning algorithms. Additionally, to each of the provided by organizers sets, except from the evaluation one, there were provided so-called ground truth tables, which contained data that should be extracted from reports. Among extracted data, it is possible to find name of the organization, address of the organization, separately city, street, and street number, names of people managing the organization with their positions, and dates, specifically date and time scope of the report. In the first step of this part of our solution, we focused on transformation of text into readable for machine learning algorithms form. As can be expected, we have decided to use a tokenizer, which is a dictionary that assigns to each word in a text an unequivocal integer number. After many experiments, we have decided to expand this dictionary with new words. The first idea was to add a base of Polish female and male names and surnames, and a base of Polish postal codes with their associated cities and streets. Both bases are available online, downloadable at no extra cost. Of course, we also thought about adding all of the Polish words, for example, extracted from word-to-vec models, but this idea did not improve our solutions. The second idea of improvement our solution was to expand not only the dictionary, but also a structure of the designed models, which at the end processed 2 types of word sequences, where one was containing the original text, while the second one was the same text, but each of words was transformed to its basic form. To extract these basic forms of words, we used an inflectional analyzer and generator for Polish language morphology Morphology. The preparation of the output vectors for an artificial neural network required a thorough analysis of the text in comparison with the available ground truth tables. On this basis, labels have been prepared associated with street, company name, date and time scope of the report, postal code, city, and people with their positions. Each of the above categories was separately analyzed. Each of the named entities like company, street, people were considered to be longer than 1 word. That is why we decided to use start word to indicate the beginning of this name in text and continue word as its continuation. We have then noticed that in the training set, there was no city names longer than 1 word. That is why we added label city. Because each of the considered companies was a joint stock company, they all had an adequate postscript SA or spółka akcyjna. That is why we have decided not to search for the sequence in text, but only for the basis of the full name, and after extraction of this basis, we added this postscript manually. Each date was separated into 3 tokens: day, month, and year. In Poland, we use 2 basic formats of writing dates, which are shown here. Additionally, in the second format, month should be written in genitive, while it is a common mistake to write it in nominative. For example, correct is 13 marca 2003 roku and incorrect 13 marzec 2003 roku. Anyway, both these versions were considered during labeling. A problem with dates was also that often the period covered by a given report was not written explicitly with dates, but descriptively, for example, the first half of 2003 or a second quarter of 2003, and so on. Due to the large variety, we did not undertake the extraction of dates from such period descriptions, thus it can be one of the considered extensions of this work. Postal codes were also considered as 2 separate tokens due to this aforementioned tokenization, which used short hyphen and long dash as filters. Additionally, we have used label O to indicate irrelevant entities. As I already mentioned, we have decided to use an inflectional analyzer and generator for Polish language morphology, Morpheusz, to extract basic forms of words. It is based on the idea that proper segmentation for Polish has to be dictionary-based, since words consisting of multiple segments are allowed. An inflectional dictionary consists of lexems, which are some abstract units of language and can be considered as a set of grammatical forms. Morphological analysis is the interpretation of words or segments as grammatical forms. It basically means assigning of a lemma and a tag to the considered word. And lemma identifies a lexem, while the tag contains values of grammatical categories specifying the form. In this table shown in this slide, an example of tagging without full morphology of Polish sentence is shown. The basic forms of words turn out to be very useful not only during labeling of the given text, but also during extraction of entities from text. It is very important to notice that we are dealing with Polish language, which is full of declensions of nouns, adjectives, adverbs, and counting words. By looking in text for a specific name, for example, Janusz Malinowski, we can fail just because there is no exact match, but there is its inflected form, for example, Januszowi Malinowskiemu. Basic forms then helped us finding the specific desirable word, but also during extraction, saving the proper basic forms of words. Polish language can be, however, very tricky. With names, companies, or cities, we wish to save their basic forms, while with streets, it is not so obvious. In this table, there are examples of text sequences with their labels to show how differently labels can be assigned. So, for example, if we want to extract street written in Polish, Marii Skłodowskiej-Curie, the basic form would not be appropriate, while analyzing part of a sentence wraz z prezesem zarządu Jerzym Wiśniewskim, we can see that the basic form is actually what we are looking for. In the next section, I will introduce you to the methods of extraction that we have proposed in our solution. As a part of each of the considered artificial neural network structure, we have used an embedding layer. Embedding is a matrix in which each row corresponds to a different word, and it assigns to it an n-dimensional vector of real numbers, thereby placing each word in n-dimensional space, thus representing an abstract distance between the words. It is possible to find various versions of embedding matrices. Among the most popular, there are those provided by Facebook FastText and by the Institute of Computer Science of Polish Academy of Sciences, which offers over 100 different models. We have performed many experiments on different structures of artificial neural networks and finally focused on two of them. The first one assumed that at the input, only the original text will be considered. The structure is on the left of the slide. While the second one on the right takes as an input both original text and the one where each word is transformed to its basic form. Let me refer to the first one as a middle and the second one as a double one. Both threads of the double artificial neural network that takes two vectors as inputs are actually of the same structure as the artificial neural network with one thread. The difference occurs after GRU layer, the gated recurrent unit, where one artificial neural network goes to the output dense layer, while the other one concatenates two threads and two additional dense layers are added. Embedding layers in both artificial neural network structures are followed sequentially with BiLSTM, LSTM, and GRU layers. LSTM, BiLSTM, and GRU layers were ruled from 128 neurons with default set hyperbolic tangents activation and sigmoid recurrent activation functions. The penultimate dense layer in an artificial neural network with two threads was implemented with 64 neurons and ReLU activation function. The last dense layer in both structures had K outputs, where K denotes number of classes, which are labels. This last layer was implemented with softmax activation function. Both models were compiled with mean squared error loss and RMS probe optimizer. As I already mentioned, in the first attempts, we have analyzed many structures of artificial neural networks. After many tests, we have decided to expand our model and design an ensemble one, which apart of the artificial neural network, took also random forest and XGBoost classifiers into consideration, thus creating a heterogeneous ensemble model. Random forest is an ensemble supervised machine learning method that fits a number of decision tree classifiers. Its great advantage is that these classifiers are trained on various subsamples of the training data and uses averaging to improve the accuracy and control overfitting at the same time. We have tested a few different configurations of random forest classifiers, and some of the results are exposed in the table showed in this slide. The OOB score is a score of the training data set obtained using an out-of-bag estimate. Prediction score is an accuracy of the prediction on the validation set. Analyzing values presented in this table, we could conclude that increasing the number of estimators did not improve the quality of the classifier, but it significantly extended the time of training and prediction. That is why we have decided to choose 200 estimators for the tests. XGBoost is a Python open source package that provides a high performance implementation of gradient boosted decision trees. XGBoost models are also ensemble ones, but they differ from the classic approach, while their ensemble decision trees are trained one by one until the error of the model does not improve anymore. XGBoost classifier was used as a meta model that was trained to output predictions based on weak learners' predictions. Ensemble machine learning model is a model consisting of multiple individual models, the result of which are aggregated in order to achieve greater prediction accuracy than for a single model. Theory behind ensemble learning is based mostly on the bias variance covariance decomposition. Bias component describes how accurate the model is on average across different possible training data sets. The variance component describes how sensitive the learning algorithm is to small changes in the training dataset. Our ensemble model, a part of the artificial neural network, took also random forests and XGBoost classifiers into consideration, making this ensemble a heterogeneous one. As it is shown in the scheme, artificial neural network took as an input vectors of words in both configurations, created from original text and words transformed into their basic forms. We also implemented two random forests. One of them was used to process vectors of words in their original forms, while the other one in their basic forms. Random forests and artificial neural network were so-called weak learners, while XGBoost was a meta model. We have also tested a configuration where another random forest was used instead of XGBoost. Let's proceed to the results. In this figure, there are shown accuracy and loss plots for considered artificial neural network models. Figures A and C concern the artificial neural network structure with one thread, the middle one, while B and D, artificial neural network with two threads, which are earlier called double one. Please notice that waveforms are drawn starting from the third epoch, while drawing all of the epochs made the plots unreadable. We have considered both artificial neural network models with different embedding matrices. NKJP abbreviation stands for Narodowy Korpus Języka Polskiego and refers to models shared by EPPAN, while FB for Facebook Fast Text Model. From over 100 models provided by EPPAN, we have chosen two ones, with 100 and 300 size of embedding matrix, while Facebook Fast Text provide embedding matrix of dimension 300. Analyzing this figure, we can see that in fact the model with one thread has better performance of training than the model with two threads, although both models appeared as well qualified. Although, based on these plots, it seems that the first one should provide better results than the second one, we tried to empirically choose the right model. Our tests consisted primarily of manual viewing of final tables prepared on the basis of the results obtained from the neural network and of capturing irregularities. These irregularities appeared in the text as unknown entities or as tokens not recognized by the tokenizer. The evaluation of the NER results involves the assessment of the correct recognition of the type of entity and the correct recognition of the word boundaries in which the entity is located. To evaluate the accuracy of entity recognition algorithms, hand text sets are usually used as a reference to the results obtained from the algorithms. There are two ways to compare the results, exact match and relaxed match. In the first approach, a correctly recognized result is one in which there is an entity type match and an exact match as to the word boundary. For example, address generała Władysława Sikorskiego, detected in the manner Sikorskiego, will not be considered correctly detected. To measure effectiveness, measures known from classification problems are used, precision, recall, and F-score. In the second approach, some blurring is allowed within the recognized expression. Recognition can be passed if the entity is included in the recognized string of words, regardless of their length. In this table showed in this slide, F-score calculated separately for each entity is presented with use of the test set provided by organizers of the contest. The last entity, people, was separated into names and positions, and F-score was also calculated separately for each of them. Analyzing this table, it is possible to notice that F-score vary between 0.41 and 0.98, depending on kind of the entity. Apart of that, we can observe that within a single entity type, each of the models gave similar value of the F-score. Summarizing our research, we have submitted 6 models to the PolEval 2020 contest, where the first attempt assumed only artificial neural networks, and the second one Ensemble ones. In this table, we are showing the evaluation scores presented by the organizers of the contest. A full description of each of the submitted models is as follows. DoubleBig is an artificial neural network with 2 threads and embedding from EPPAN of size 300. 300XGB is an ensemble model with XGBoost and embedding from Facebook FastText of size 300. Double Small is an artificial neural network with 2 threads and embedding from EPPAN of size 100. 300RF is an ensemble with random forest and embedding from EPPAN of size 300. Middle Big is an artificial neural network with 1 thread and embedding from EPPAN of size 300. 100RF is an ensemble with random forest and embedding from EPPAN of size 100. Analyzing our results, trying to improve them while browsing available documents, we have noticed that not every entity appears in the considered financial report. This fact, together with the notion that we are dealing with entities of the multi-word expressions type, and due to the specificity of the Polish language, makes the presented issue of NER very complicated. It is necessary to remember that Polish is an inflectional language, and the task of named entity recognition is much more complicated than for example, English. In the literature, it is possible to find F-score values of 70 to even 95%. However, it should be emphasized that these studies are limited to carefully selected categories of NER, usually the ones that give the best results. And the algorithms use frequently hand-created rules and lexicons. At the end, I would like to add that we are still working on extending the proposed solutions, and I can confidently say that the results have already improved. Thank you very much for your attention.